Well, thank you very much for that overly kind introduction. Certainly, I was very flattered. So that put me off, of course, a little bit. So let's start the talk. I want to cover the area of computational sciences, and I will try to keep it as general as possible and try to delve as little as possible into technical issues. If I stand here, it's not because of my own merit, but because of the merit of many people that I have the good fortune to work with over the years. And I just want to acknowledge a few of these. First of all, the people that comprise the GMU CFD Center. And I've put a couple of names and the areas of work there. There'll be a test at the end of the talk as you remember all those names. The people from SAIC, which carry out a lot of these sensitive runs that are of importance to national security. Some other groups across the country, from San Diego, from the Naval Research Lab, from Inova Hospital, and some university links that make sure that what we do here has standing on the international level so that we don't become too provincial. Here's an outline of the talk. There are three basic questions I want to cover tonight. First one is why computational sciences. The second one is why now. And the third one, whither now. So the first question is going to try to answer the areas of creation of information and insight and how computational techniques are being used today in science and engineering. The second one is going to look at the enabling technologies, and we're going to exemplify those in the case of computational fluid dynamics, but you will see that those carry out to any of the other computational disciplines that have arisen. And then where do we go from here? What is the current status? How can we extrapolate from current trends? And what are the implications? So why computational sciences? Well, let's go one step backwards. Why information? Why do we want information? Why do we want insight? Why do we want knowledge? And the first answer is that we're human. And one of our traits is that we're curious. It's one of the things that sets us apart from apes and other animals. But then there is a very important need, which is the need to predict. If you're building a new aeroplane or a new car, you want to make sure that that aeroplane or car is working by the time you build it. Another area where you need to predict is intelligence gathering. What happens if this happens? What is the outcome if I do that policy change, or if I drop this weapon in this place, or whatever it is? And then there is the need to post-dict. If something has happened, can I explain what has happened? Okay. And of course, forensic analysis is just one of the areas. So you see information appears there everywhere. We can exchange information, insight, knowledge. All of these are synonyms, and we can have a long debate as to what the difference is between those, but really it's information gathering in the first place. And really information is the gold of our times. I went through the list of Forbes' 100 richest men, and if you look at the first 27, you will find that at least 11 of them have directly to do with information. They either enable it, they evaluate it particularly well, they build the hardware for the information or the software or the search engines or whatever it is. Now, there are a few other ones, notably the three Walton heiresses from Walmart. And if you look at what Walmart's chief competitive advantage is, it's the extensive and intensive use of information technology. That's one of their key advantages as compared to other retailers. So you could add another three to this one. Now, if we look at the engineering sector, and we live in a technical age, so I think it is proper to look at this. If you look at the product development cycle of any given consumer product, you go through different stages, and I've drawn three curves there. As you go through those stages, you will see that some of these drop and others climb. The one that drops is the possibility of change. when you haven't built anything, when you haven't decided on anything, when you haven't frozen any designs, you can build whatever you want in your mind. But once you have preliminary design become detailed design and you commit a lot of resources, the possibility of change diminishes drastically. When you get to prototype testing, that prototype better work, otherwise you've basically lost either $4 billion if you do a car or $20 billion if you're building a new aeroplane. That's more than several years' profit. So you're literally betting the company in many industries on your next generation product. And so it is extremely important to know at an early stage if anything is going to work. And you can see the effect, or let's say one of the drivers of doing this computationally, is that before you bend any tin, you have as much information about your product as possible. And that's the light blue curve that is trying to push the amount of information that we know, the information content that we have of our product, as early as possible to as high as possible a level. Now, how do we create information and insight? There are basically only 4 ways of doing this. One is to assimilate data of what has been done before. You go back and you look at your competitors and you look at all the products that have been built that are similar before, and you try to figure out a trend line, or let's say a sweet spot where you think a good design is. The second option is to do classic analysis, and I'll talk a little bit more about that in the upcoming slides. The third option is to do experiments, either with models or prototypes. And the fourth one is to do computational or numerical techniques, or virtual experiments, as they are also called. Now, all of these 4 have progressed rapidly and are still progressing. And I'm only going to highlight the last 3 just to contrast their pros and cons. If we take classic analysis, we're trying to derive a basic equation. In most cases, it's going to be a partial differential equation that is going to describe nature, but it could be an ordinary differential equation if you think about population growth or some other kind of battle management problem. Yeah? And this gives you the most condensed form of information. And by knowing what the trends are or the exact solutions of that equation, you gain knowledge from this solution about what to expect from the behavior of these solutions in the future. Problem, of course, is that in almost all cases we can't solve these equations analytically. Some famous equations, well, the inviscid flow equations derived by Euler 1760. For viscous flows, air, blood, water, oil, Navier and Stokes, so approximately 160, 170 years old. Maxwell, electromagnetics. Einstein, I guess everybody knows the equation I've put up there. But there are others, Schrödinger, Heisenberg. These are, let's say, you gain immortality from an equation. Once you've derived that equation, your name is forever part of the human lore. And let's say deriving these equations is the closest thing to the Platonic ideas. Yeah. Once you have that partial differential equation that describes a flow, an electromagnetic wave, a quantum mechanical field, whatever it is, this is as close as you get to nature. This is how God decides nature is going to be. Yeah? So you're trying to understand God in a way, and if you look at the diaries of famous physicists, you will see that really this was one of the ways they interpreted this. And another part that happens is that once you derive these equations, there's an almost indescribable acceleration. And a good example is Heisenberg, when he derived his equations, and he was on a ship to Helgoland, one of the islands in northern Germany, and he describes this very vividly in one of his memoirs, where he saw the sun rising, and by that time he had derived these equations and everything became clear in his mind. And it's sort of an almost it's a very, very moving moment. So if we want to, let's say, reduce or summarize this, a good way to summarize this is what Goethe says in the Faust, written 1808, end of the metaphysics era. And if you want, I can read it in German, but I have a translation in English for those who don't speak German. But ye, the gods' true sons, delight in living bounteous beauty, and what floats in wavering appearance, fasten in lasting thoughts. So you can see again the connection here to the Platonic ideas, things that move and you want to hold them into what is the most condensed form of information. Now there are problems with this. These equations are solvable only in the rarest of cases. They're solvable only for very simple boundary conditions. And if you look, for example, at fluids, there are only 6 known exact solutions for very trivial flows. So anything that has to do with anything complex geometry, say flow in an artery or flow past a car or flow past an aeroplane, is not solvable in an exact way. So you need numerical methods. Second option to gain information or insight or knowledge is to do experiments. And these are the steps that you will go through if you do an experiment. Famous experiments. There's a whole list of these, starting from Galileo, and you can also regard the atomic bomb as one of the great experiments of science. Basically, you can also gain immortality from experiments. Certainly Galileo and Torricelli and Hertz did. And it's really regarded as the unequivocal truth. Really, there's nothing you can doubt about an experiment. You can doubt about the experimental device. You can doubt as to whether you measured what you're really trying to measure. But once you have answered those 2 questions, what you measured is what is happening. What are the problems with experiments? Well, we can't do experiments for all things. If we want to recreate the origin of the universe, that's a kind of difficult experiment to do. The same with nuclear weapons, the same with fusion, the same with biomedical devices. I mean, how many people do you want to kill until that device works? Yeah? Second problem that we have is that they are inaccurate. The real size experiment, let's say if I wanted to simulate a bomb dropping from an aeroplane, I have 3 non-dimensional numbers, as they are called in physics, that I have to obey. The Reynolds number, which is the ratio of inviscid to viscous forces. The Froude number, which is the weight of the aeroplane compared to the forces that the air has. And the Mach number, which is the speed of sound related to the speed of the particles, or the incoming velocity. Now, it's very difficult in a test chamber to reproduce all 3 non-dimensional numbers at the same time. So you will always have to compromise, and that will introduce inaccuracies in experiments. And it's not the only case. If you're doing flapping of bridges, if you're doing all sorts of things that are to model scale, you will always have that problem, because you cannot obey all non-dimensional numbers at the same time. The third problem they have is that they're costly. In many cases, wind and water tunnels are not available, and the test evaluation can take a lot of time. In some cases, you destroy the equipment you're testing. It's happened a lot. Typical case, the testing of atomic weapons. It's untimely, particularly if you think about consumer products where time to market is absolutely critical. An aeroplane that gets to the market 12 to 16 months late is about $100 billion, one side or the other. Yeah, so it's absolutely crucial to be in the market at the right time. The other problem that you have with experiments is that you have a lack of detailed insight. You only can get measurement at certain points or on certain surfaces, but it's very difficult to get information over the whole flow field, or if it's a mechanical piece, the whole displacement field or distortion field or whatever it is. And lastly, and this is very important for engineering or for the next generation product that you're trying to develop, if you do an experiment, you only get information as to this is how it is, but it doesn't answer you any question as to how do I make it better. So there's no optimization guidance whatsoever. So why computational sciences now, which is the 4th alternative? Well, first of all, we can do a lot more because we have learned how to solve the proper physics, and we have learned how to couple physics from different fields. Secondly, we have improved algorithms drastically over the years. We have reduced setup times, and we have continuing advances in hardware. And I'll go through these in some more detail. So a typical bottleneck for field solvers was advection. Advection are typically first-order partial derivatives. Okay? And in 1959, there was this very heavy theorem that Godunov proved. No linear scheme of order higher than 1 is monotonicity preserving. So even if you have a linear equation and you think you are formally of high order accuracy, you really have to solve it with a nonlinear solver. That was a huge change in mind that had to take place and led to a whole series of new solvers. So these were your options to solve this equation in the 1960s. This line here is the exact solution, and basically this same profile should reappear time and time again. It's basically you're just advecting this down. Imagine you have a cloud of some toxic material, and in the presence of any diffusion, that cloud is just moving. Okay, so that's the cloud here. That's the concentration. Now you had two options. You could either go first order, you can see it's overly diffusive, or you could go higher order, and you can see you get all these non-physical wiggles. Now imagine this is a temperature, and you have an ignition point in a combustion engine. What would happen here if you get these overshoots? You would get totally irrelevant solutions because it would spark too early. Then came the 70s, and this is the first nonlinear solvers that appeared, and you can see we're doing a lot better. We don't have any over or undershoots, and we are approximating the solutions much, much better than before. And in the 80s, we finally got a handle on this, and you can see these are all very good solutions of these tough problems. Second bottleneck that we had to solve algorithmically was mesh size. Because many problems are characterized by very small regions where you have extreme changes in the solution, where you require a very fine grid. But overall, there may be other parts of the flow field, but nothing is happening. So we only want to use a fine mesh in these regions, but we don't know where these regions are, so you need adaptive mesh refinement. And I have a typical case here. This is a blast going over a wall and hitting this back building here. So the blast occurred around here. And you can see here the physics, and you can see here the adaptive refinement. All these black lines here are tiny elements that have automatically refined. And this is something that happens every 5 time steps automatically. The third problem that we had to overcome is to get the solutions in a reasonable amount of time. And so it turns out that for very large problems, and large is of course a relative term, by now we're solving 10 to the 11 grid points, but say above 10 to the 7, iterative schemes are faster, and if you're not careful, this can take a lot of time. Luckily, bright minds came up with fast solution techniques, and this is a typical case here. This is a landing configuration, and you can see the typical wings that are spreading. And if you did this with an ordinary solver, you would compute forever, whereas if you use one of these advanced solvers, you converge relatively quickly. So you have huge advances there. And perhaps the biggest of all I've left for the end, which is Moore's law, which says that computing power doubles every 18 months. Okay? Now you can argue whether it's 18 or 19, but if that happens, and of course if you're a student, 18 months is an eternity. Once you reach 40, 18 months just flies by, okay? So these computers double so quickly. Yeah? Now it's interesting to note that the term supercomputing appeared around 1980 with the introduction of the Cray supercomputer. And ever since then you can see we've gone up 5 orders of magnitude in speed. Now, this is a number that I wish you would remember. Every 5 years, we improve compute power by a factor of 10. So if it takes us 2 days today to compute an aneurysm to very fine detail, it means that in 5 years it's going to take 2 hours. And in 10 years, it's going to take 2 hours divided by 10. Okay, so it's going to be 12 minutes or something like that. And you can see how this is going down in time. So, if we get more transistors, we get more cache, and of course you can see continuing improvements also in the clock rates, the prefetching, branch prediction. These are all technical terms, but basically what they do is they make your computer faster. And the prognosis here is that this will continue for at least another factor of 100. Now, if I combine these, you can see that the improvements due to solvers, due to algorithms, and due to hardware are all compounding. So the gains that you get over the last 2 decades are either of the order of 10 to the 5 or 10 to the 10. Okay? So if you think, for example, about car manufacturing, by how much has car manufacturing improved over the last 60 years? A factor of 3, a factor of 4, maybe a little bit more, but certainly not a factor of 100,000 or 10 to the 10. When something like that happens, you get what is called a Cambrian explosion, which is what happened in the history of life. When there was sufficient oxygen, then all these multi-celled animals appeared. It's the same here. When you get this much improvement in something, you create a new field. And that field is computational sciences. Okay? Because that opens new possibilities, it opens new markets, and it leads to a lot of economic growth. The current computational mechanics market alone is $10 billion, which of course is peanuts compared to what Microsoft is doing, but it's growing at about 20 to 24% a year. So we still have room to catch up. Now, because you had this Cambrian explosion of possibilities, you get suddenly the computational sciences. And they mirror the classical disciplines, but offer a lot of novelty, as I hope to show. In fact, they have become the band that unites interdisciplinary endeavors. Now, each one of these is there are families of these. For example, you could take computational physics or chemistry or engineering, and under computational physics, you could put computational astronomy, perhaps, but not quite, because suddenly, if you do computational astronomy, you can do computational chemistry as well. Okay, so the next stage, when you go into these stars and you want to get more details, suddenly involves chemistry, perhaps, yeah? Or some other phenomenon, electromagnetics, jetting, all of these other effects. And then under computational physics, you could also have computational fluid dynamics, and under computational fluid dynamics, you could also have computational aerodynamics, which is a field on itself, computational aeroacoustics. If you go to any of the AIAA meetings, you will see that there are whole sessions devoted to this, computational bubble dynamics, etc., etc. And of course, it should come to no surprise that we have computational geography, computational climate dynamics, computational economics, computational social sciences, etc., etc. Now, what have these virtual experiments given us that we couldn't do with the traditional experiments? Well, first of all, they make a lot of experiments possible, unless the physics is not understood, and in that case, they're used to understand the physics. They've given us accuracy because we solved the real problem that we have, not some scaled-down experiments where we have to compromise with non-dimensional numbers. They are cost competitive because the setup times have increased or have been reduced drastically, and because the algorithms, the software, and the hardware are still improving. They are timely because I can simulate and compute before I'm bending tin, before I'm producing whatever I'm doing. And they give me detailed insight because I compute 3D fields. I don't just get a pressure probe or some marker particle that I'm measuring. I'm getting the whole information. Yeah? And finally, they give me optimization guidance. So you can see all these disadvantages that we had with traditional experiments, we've been able to overcome with this. Now, let me explain a little bit more how this works. It is a multidisciplinary science because you have all these elements that are coming into play. And I'll start with engineering because that's the reason why most of these runs are being done. After all, we are a technical society. From the engineering, we have to go over to the physics, and physics gives us what are the relevant phenomena, what are the possible approximations that we can make, and what are the characteristic partial and ordinary differential equations. So we might end up with something like these, which are the flow equations for incompressible flow. Next step is we look at these equations and go back to the mathematicians And first, overall, we do classic analysis. So we look at existence of the solution, long-term stability behavior, what kind of Sobolev spaces do these solutions live in, etc. Then we have to go to numerical methods and analysis to solve them. And then we also have to go to discrete mathematics to actually solve them efficiently. If I gave you the task of computing the square root of 2, how many of you would be able to compute it to the 10th decimal by hand, just with a pencil? After we have that, we go over to software. So we go borrow from computer science. And this involves not just the algorithms that code what the mathematicians have told us that we have to do, but we also have to get the software and the hardware part sorted out, because otherwise we may have a very nice algorithm that runs very inefficiently on the machine that we're trying to run. After we have the runs done, we have to visualize the results, and this involves optimal algorithms, ways of seeing, and of course developing new tools for discovery. Finally, there is a human aspect, and these are the users. They have to be confident that this software is good, so there has to be a long process of benchmarking, quality assurance. We have to educate the people, motivate them, and we have to overcome things like the not invented here syndrome if this software is going to work in other places. So you can see this is a rather interesting chain, and of course it's only as strong as the weakest link. So it should come as no surprise that whether you do computational fluid dynamics or structural dynamics or electromagnetics or whatever, it involves a series of talents that you have to put together. Now, what has the impact of, for example, CFD been in our daily lives? If you look at the hours of wind tunnel testing for a configuration development, you can see here the number of wings that were tested for the 767 and the 757, and you can see when we come to the 787 right now, we are down from 17 to something like 5 wings. We're not going to test more than 5 wings by the time this thing is actually built. And let's say these effects have been even more dramatic if you look at the integration of engines. This integration of the engine is sometimes very tricky. The early 737-300 had really severe problems of interference, so there was a huge drag increase due to the presence of these nacelles. And you can see here the number of tests that had to be done really are reduced from 50 to nothing. Many engines today go directly onto the aeroplane before they're even tested. Now, if you look at the number of wind tunnel hours that we have for new airplanes, you can see that we have reached a plateau at about 10,000 wind tunnel hours. And the wings are getting more complex, but of course all of this increasing trend has been ameliorated by the wind tunnel plus the computational fluid dynamics. Now, are we there? No, by no means. You can see here an extrapolation to the year 2030, and really if we want to get for a single configuration, we need about 75,000 runs, and if you think that we're going to do it in a reasonable amount of time, you will see we need machines that are about 3 orders faster than a petaflop machine. Right now your Pentium is running at about maybe 500 megaflops, so orders of magnitude faster. Now, what discoveries or what developments are attributable to the computational sciences? That's a question that I think is on everybody's mind. If I look at mathematics, there are 2 theories that have swept over the community over the last 15 years that were only possible because these people had computers. One of them is chaos theory and the second one is wavelets. These 2 mathematical fields, they've really grown into fields right now, are only thinkable and are only doable if you have some kind of a computer. Otherwise, you can't test any theories, and you can't do any statistics, you can't get anything out of it. Then there is the supercritical airfoil. One of the reasons that airplanes are so economic today is that particular airfoil, and this is an interesting anecdotal history. This happened towards the late 70s, and at a congress, a very famous experimentalist from NASA Langley came up with this shape at the same time, the Dutch had computed this shape before putting it into an experiment. Of course, the Americans wanted to have a patent on this. But of course, it's hard to have a patent on gravity. So if this airfoil comes out of a mathematical algorithm, can you get a patent on it? Not so clear. Okay? Now, if you think about the current generation of semiconductor wafers, which are about this diameter, they're only possible because while you're manufacturing them, you're computing what the flow inside looks like. You have measuring devices, and then based on that flow, you monitor and you change the heat flux so that that flow is perfect for the creation of super pure crystals. And going from the earlier diameter to something that is double, and that of course reduces your economic cost drastically, was only possible because you're doing CFD runs at the same time. And then one of the recent things that our group has come up is the clinical relevance of hemodynamics on aneurysm rupture. And again, that would not have been possible without computational sciences. So, this is how it is. Now let's see if we can predict a little bit about the future. So, a word of caution before we start with that. To predict the future from the present is typical of human behavior, but it's only proper unless some disruptive technology event occurs. And in this field, a lot of these tend to occur. There might even be disruptive events within departments of a university, but that's a different matter. So, and of course, chaos is a part of living beings. So, we should not take the humans out of this equation. So, human can be very disruptive as a technology. Now, I mentioned that all of these comprise the computational sciences. And so, what are the trends in science and engineering? It's used extensively. Software vendors are part of the process and the supply chain. So if you're sitting at Ford, you're continuously expecting new CFD, new structural, new thermodynamics software that is coming in to help you design that new car. And you, as a user, are continuously pushing these people with your demands. Put this in the code, I want to simulate that, etc., etc. So it's a symbiosis by now. Okay. We have a healthy mix of packages in all fields, which comprise commercial, government, and in-house packages. And it's a very healthy competition. And all these packages have many levels of fidelity. Now, they've all reached a fairly high degree of maturity, and I've just put a partial list of what is in these codes. And just by the length of the list, you can see that putting together one of these codes, which typically has anywhere from 1 to 5 million lines of code, is not such an easy matter. If you look at the physics, in all the fields we have increased realism. So we're trying to bridge now from continuum to atomistic scales. And I just want to concentrate on two here, the flows and the structures. Basically, if you look at the acoustic fluctuations, they are 10 to the minus 6 of ambient pressure. If you want to simulate that accurately, you need to have extremely good solvers, or you have to reduce the equations. Combustion is another area. You have many species, a very important part if you want to have a cleaner running engine. And if you think about multi-phase flows, things like cavitation, bubble dynamics. Look about structures. The continuum equations are very well established. We've known those, but the problem is what happens if we have failure, cracking, spallation, or the treatment of discontinua, like concrete. If you try to blow up a bunker, this is something you really want to know. Now, if you look at the numerics, the solver research spans 5 decades, and I've listed here some of the improvements, but with any new generation of hardware, we have to go back and rethink the algorithms, at least a part of that. So if we look at Moore's law, today's supercomputer problem will reach the PC in 15 years. And so that means that in the next 5 years, on a PC, you'll be able to solve about 100 million elements. And on a supercomputer, you might be able to solve 10 to the 11 elements in the next 5 years. Now, if you look at the advance in games and graphic cards, that becomes now an interesting option to push computer power. What are the current bottlenecks? Well, we have in each one of the areas here pre-processing, the cleanup for dirty complex geometry. So suppose you're given a whole car by a designer. Now do me a quick run. not so easy. Grid generation, optimal boundary layer grids, particularly for walls and wakes. If you think about flow solvers, reliable implicit solvers, this is not just flow solvers, but any kind of solver. When you do implicit solvers, you can generate what is called the dynamics of numerics. So it's a very tricky area, and it's an area that is unsolved and where perhaps mathematicians should take a look at again. Post-processing, it's really the vast amounts of data that we're generating. For example, at the Missile Intelligence Center in Huntsville, one of our codes is generating approximately 85,000 runs a week. Now, if some human has to look at those 85,000 runs, he better have some software tool that helps him through it. And if you look at optimization, we have some really difficult theoretical issues to tackle, mainly this one theorem here and the hierarchical representation of data. So now let me extrapolate. First extrapolation is we're going to increase realism. I think that's an obvious one. The second one is that we're going to be more interdisciplinary, and I've just listed here 3 possible spaces: structural dynamics, fluid dynamics, and thermodynamics, and some of the areas that are encompassed by the combination of these. And here are some of the applications that go with it. So anywhere from chip cooling, parachutes, tents, high-performance engines, aerodynamics, or flutter, and so on. Second extrapolation, we're going to use concurrently many algorithms and many codes. So for example, if you want to simulate a bomb dropping all the way into a bunker blowing up, some nasty stuff in there, the cloud of this toxic material then propagating down, you will have to use for that optimal algorithms, and you can see here the type of algorithm that you would use for the fluid and for the coupling to the structure. Now this is not just for this application, it's going to be throughout a vast range of applications. I've just brought this up because it's, I think, a very visual example. But it brings up the third extrapolation, and that's the extrapolation of user qualification. Because computational packages have become so sophisticated, they offer a vast range of models and options. So you as a user need to decide what model, what geometry, what grid resolution, what relevant diagnostics. A lot of software tools will be given to you to help you make that decision. And of course, ideally, we would like to have all this automatic, to which I will say, you don't want to have an idiot doing this. You want to have the highest possibly qualified individual there. Yeah? Because you have all these options. The damage that you can do with these codes in doing bad runs is also substantial. Yeah? So there are 2 possible ways out of this. One is that you have these very refined shops that do these runs, so you do an outsourcing, or you look for higher education institutions like ours and try to qualify individuals that way. In fact, if I look at my list of students in CFD, a lot of them are from the labs and the agencies in this area. And they're precisely here for this reason, because they want to know more on how to use these packages efficiently. Fourth extrapolation, we're going to demand higher solution quality. It's a logical demand. After we can do the physics and we have the right realism in the codes, we want to demand a higher accuracy. We want to say, give me the result. I want to have the drag on that airfoil to plus minus 2%. And guarantee me that the result that you're giving me is within those bounds. Not so easy. You can also think, I mean, an airfoil perhaps is a very abstract example, but suppose you have an aneurysm in your brain. You've been diagnosed with that. Wouldn't it be nice when you go and see the doctor that you can get a flow calculation of the blood in your brain to within 2% accuracy? Suddenly accuracy becomes very important. Yeah. The fifth extrapolation is that we're going to look at solution sensitivity. Again, it's a logical demand. Once we have something that is accurate, we want to know if I turn this knob, if I change my viscosity or this inflow condition or this geometry factor by so much, what is the effect on the solution? Sixth extrapolation, we're going to use computational sciences to design experiments. Why? Because experiments have become more and more expensive. And in many cases, we only have one shot at a large-scale experiment. So we have to make sure that the experiment is successful. So we're going to use calculations before the experiment is done to tell the experimentalists where to put the probes, what to expect of the experiment, and what probes go in what places in the most efficient way. And in fact, if you look at the folks at SAIC that use some of the software we have developed here, 90% of blast structure runs are pre-experiment runs. There may be a few runs after the experiment is done, but all the possible scenarios, and of course also all the diagnostics that are given to the experimentalists, are done largely before the experiment is done. Seventh extrapolation, we're going to use this a lot within design and optimization. Again, it's a logical step. If we can compute something, we have the ability to optimize it, right? And there are two things that you may want to optimize. One is the shape. So just have an optimal car shape or optimal engine shape or an optimal airfoil shape, or a process. Think about Hershey's producing chocolate ice cream. Yeah. That's $1 billion a year. If you can get 10% more out with the same input of energy, wouldn't you go for it? So that's a typical process. You can think about steel mills, you can think about extrusion, food production, all of those. So this is a very important differentiator with respect to experiments. In industry and science, the penetration is limited, but it's increasing for obvious reasons. But there are several outstanding issues here, theoretical issues. First of all, what is optimal? In many cases, an engineer will not know what is optimal. So this might be a way of helping him find out what really makes his product good or not. Then what optimization strategy should be used? You may have continuous functions or may have discontinuous functions. How do you put this in a hierarchical design so that when you know very little of your object or your product or your process, you have a very coarse representation, and as you know more and more and more, you put more and more detail into your model in a hierarchical way. How do you integrate this into the chain of processes that occurs in industry? And then there is this theoretical question as to how expensive is it? And there is this theorem that appeared a few years ago, which says that if you have n design variables, you need to do an n multi-point design. So if I'm designing an airfoil, and this is a typical drag curve for an airfoil, so close to the speed of sound of 1, Mach number, so close to the speed of sound, there's a huge rise. And of course you want to fly as close as possible to there, because the faster you fly, the more economical it is. But a good design would be this yellow curve. A very bad design would be this one here. Now I could be designing optimally at this speed here, but I would be very bad in this region. Now what the theorem says is that if you want to have this robust design curve, you have to design not just for this speed, but for all the intermediate speeds, and the number of intermediate speeds that you have to design for is equal to the number of design variables. Now just as a reminder, the B777 wing has over 7,000 design variables. Okay, so you would have to do 7,000 different speeds and design the airfoil for that. Obviously, that is not what Boeing did. They wouldn't have finished the airplane by now if they had to do that many runs. Okay? But what is important is that this is sort of the lower bound given by by something that is provable mathematically. Okay? And it's really a big problem on how to make this practical if you look into the future. How are we going to use hardware? This is my 8th extrapolation. Anything that is less than 50 million elements, we're going to use some Linux farm for this, because it fits on each processor. Anything less than 500 million elements, we're going to do on some shared memory supercomputer, and everything that is above that, we're going to use on some multiprocessor machine, if that multiprocessor machine has the right interconnect, which makes it an expensive machine. Now, 9th extrapolation. I only have 10, so bear with me. Okay. It's an evolving work environment. As we look into the future, we will see many, many runs. I mentioned this one example where we have 85,000 runs a week. Right? So you want to have some kind of way of not overburdening the user with this, so you want to have a minimal user input for these many runs, and so that you have these scoping or these stochastics or these envelopes that develop there done automatically. You want to do this in a distributed computing environment, and then you want to assimilate the data as logically as possible, because in the end, all what we're doing with these runs is getting data, which we're then processing into information, which we then try to put in some intelligent form so that somebody can make a decision. And of course, if you go down the range here, the higher you go in policy making, the lower this protocol has to be. Okay, so if you're going to the Undersecretary of Defense and you're showing, a pressure plot over time, that's not going to fly. He just wants to see the destroyed building. That's the decision he wants to make. Okay, so as an example of this, I want to show one case here that comes out of our group. We put together this database of aneurysm models. There are about 120 patients from INOVA in this database, and you can see here all kinds of different aneurysms that were actually computed. So you see the flow in here, the shear stress, the flow patterns, and out of this you can try to see if there is some correlation between the flow patterns that you're seeing in these aneurysms, which you have computed. They were never measured. Yeah? All what we have is we know that for in vitro or for other experiments that were done, that these calculations are correct. But these 120 patients, there was no way we could experimentally measure them. We got the inflow and the outflow conditions, but the 3D flow field was computed. So out of these calculations, you can now get statistics, and you can get relevant statistics whereby you can relate the macrofluidic behavior that you have in the aneurysm to the probability of rupture. So with that, you can answer the question, which patient has to be treated? Which is a very fundamental question, given that every second person will have some kind of treatment in the years to come. 10th extrapolation. If we extrapolate Moore's law, you can envision instant computing. So now CFD, instead of being a burdensome thing, is basically buried in your life, and a lot of concurrent computing is being done as processes occur. So first, it will be, of course, every engineer's dream. I just change the shape of a car a little bit interactively and then immediately get the flow field or the acoustic field or whatever it is. The second one is the process control. I already mentioned silicon wafers, but you can think of many other processes. You can think of flight mechanics. Imagine flying transatlantic. You have, 8 hours or 6.5 hours, depending which way you go. That's a lot of time to compute. As the aeroplane is getting lighter, you could bend the shape of the wings in such a way that you have an optimal wing all the time. You could have battlefield strategies where you have on-the-fly targeting, patient-specific evolving medical devices. So not just compute the medical device right now, but have a little monitor that goes on, and then as the artery is regrowing or some other biological process is happening, you're computing at the same time and adjusting the stiffness of your stent or some other thing that you want to do. And of course, responses to natural. But there are many, many other applications that you can think of. So, I want to conclude with a few visions of the world. The first vision is the question of what is real. What are the limitations of us knowing about nature, knowing about the world? Well, we said that experiments were the absolute truth in the empirical sciences. But any measuring device will have a predisposed output and a predisposed error. Not only that, you can't measure that accurately because physics tells you that you can't. You have the uncertainty. So you can only measure to that accuracy. So if, for example, you wanted to measure pi to 32 digits after the comma, There is no device that will measure pi. It's only something we can know because of theory. Now, analysis, when possible, is the description of nature that we have, but the problem is with the realistic boundary conditions. If we have virtual experiments, we have basically the starting point the same as the analysis, although you could also start from particle models or other models that are not describable in classical terms. But you have this problem, or say the numerics employed and the number of degrees of freedom that could predispose the output. And of course, your visualization, which is the same as the measuring device here, could also predispose your output. So what is real is something that will haunt us and something that we will have to critically examine always. So, is the world an equation? That has been the quest ever since Newton and Leibniz developed calculus, no? Or Galileo did his experiments. So, what can we say from these equations? Certainly, they describe the fluids. They are the most condensed form of information. But do they explain everything? For example, for these equations, there is still $1 million prize for those who can prove that there is a unique solution that is stable. It's one of the 10 unsolved problems that were posed at the beginning of this century. And secondly, if you look at turbulence, tonight when you wash, just open your faucet softly and you will see that the flow is first laminar, and then when you blow it, when you keep opening it, you will see that at some point it becomes turbulent. To describe that turbulent flow field is still an unsolved matter. And these equations by themselves don't solve that. Well, there's a third world, which is the world as an algorithm. And this book came out a couple of years back. And there's an interesting theorem in there, which is provable, which is basically that the descriptive power of very simple algorithms is infinite. So any given process in nature can be described by an algorithm. And after all, if you do computational sciences, you're doing calculations. So we can describe numbers of processes or phenomena from algorithms, but the problem is, if you see the world as an algorithm, which algorithm? And why this algorithm? So what has happened to insight? We have learned over the last 200 years to gain insight from here. We're just at the beginning of gaining insight from this. Now, I would not regard this as, let's say, I would say this is one of the delusions of computational sciences, but because it really explains very little about nature. But there is serious work also that tries to get to that. So, my last outlook slides. First of all, computational sciences has always been interdisciplinary. It's a chain of events, a chain of disciplines that hold together, and they will only be as strong as the weakest of those links. We have 3 to 4 decades of development, but really supercomputing started around 1980, or let's say the birth of computational sciences you can trace to the Cray 1 machine, I would say. There's a vast amount of software out there to do this. Highly specialized solutions are emerging for very specific areas. Multidisciplinary optimization is becoming a reality. And, of course, multi-length and multi-timescale optimization. I mean, if you think about a medical device, for example, the flow happens in the order of hundreds of seconds, but this thing is going to be in the patient for the next 20 years. So you have huge ranges. In other cases, protein folding. Things that happened on the atomistic scale happens in nanoseconds, but you have to integrate that to several minutes in time. Now, what we will see is that all of these computational tools, or these computational sciences, will be embedded in many products and processes, and we will have physics-based virtual reality. So in that sense, it has become truly a pillar of the empirical sciences. Most experiments, and particularly the large-scale experiments, will be preceded by lengthy runs done either for the fluid or the structural or thermodynamic, electromagnetic or multidisciplinary part of this. And of course, that can yield to biased insight. As far as computational sciences are concerned, it's, as I said, the new pillar of the empirical sciences. It's a new way of seeing reality. And it's a new way of measuring, seeing, understanding, or going where we could not go before. And the task for philosophy is, and I think there are some philosophers here tonight, is to think if we need a sequel to Kant's Kritik der reinen Vernunft, which analyzed the empirical sciences at the end of the 18th century. So, I leave you the choice. Is it going to be Zarathustra's vision of the last human, which really only does experiments and cannot raise his sights to higher levels? And I've just quoted a part of that. The earth has then become small, and on it hops the last kind of human, the one that makes all things small. His stock is uneradicatable, like the flea. The last human lives the longest, so everything is just bean counting, numbers, and Wall Street. Or you really stick with ideals, and you try to increase knowledge, and you try to capture in ideas or in knowledge what is really happening in nature. And of course, I see our mission at George Mason University in that latter category. Thank you for your attention.